Bismillahirrahmanirrahim. Assalamualaikum and very good day to you all. In this video, we are continuing about the chapter 11.4 from the book Shigley Mechanical Engineering Design. We're talking about bearing, and chapter 11.4 talking about reliability versus life, specific on Weibull distribution. Okay, so what is a Weibull parameter? Weibull distribution, the same as Weibull parameter. Okay. So the Weibull parameter basically is a parameter to do prediction. Okay, you can use this Weibull parameter for all application, meaning that it's not only limited to screw. People have done it throughout the years. Even historically, Weibull parameter has been founded during World War II. Okay, people predict when the machinery, the war machine, their tanks will be damaged. How many prediction? What? How many tanks may damage? How many people may lost in the war? Okay, historically people have done this using Weibull parameter. They can predict. You can find this information from internet. Okay. Uh, Again, Weibull parameter. Uh, People who are doing this, the statistician, mathematics, they are better in explaining Weibull parameter. We in this topic, only part of it, uh, we are using the the reliability function that we can so that we can predict when this bearing will fail, when this bearing may fail. This is what we predict, so that you can choose the suitable bearing for you. Okay, so let's continue. The Weibull parameter as constant load. At constant load, the life measure distribution of rolling contact bearing is right screwed. Here, you see, right screwed. Okay, like this. Okay, because robust ability to adjust the varying count of squeenness, the three Weibull parameter distribution is used exclusively for expressing the reliability of contact bearing, which is exactly 10 percentile, 15 percentile, and 90 percentile. Okay, 10, 50, and 90. Okay, so Weibull reliability, unlike the development of normal distribution, okay, we will define the definition of reliability for a Weibull distribution of the life measure. So for normal distribution, you have learned in your mathematics class, you have learned in your mathematics class about the bell shape like that. Okay, this is normal distribution. Okay, you have learned in mathematics, but for Weibull distribution, the graph will be somewhat like this. Okay, this is a graph, normal graph for the Weibull distribution. So okay, mathematicians know better than me. Okay, so the reliability expression for reliability R is exponential x minus x naught theta minus x naught power of b. So x, the guaranteed or minimum value of x. Theta is characteristic parameter for contact rail bearing. This corresponds to 63 percentile. B is the shape parameter that control the squeenness. The parallel contact bearing B equals to B approximately to 1.5. If you ask me how you get this value, better ask people who are more expert. Okay, uh, we just use I just use this equation. Okay, I just use this equation. You also use this equation. Okay, Weibull reliability for line measured expressed in the measureless as form as x equal to L over L naught. Remember, L is the life in revolution in hours. Okay, this is definition of life for bearing. Okay, L equal to life equals to hours. Also, life equals to revolution per minute. This is what defined by life. So L10 equals to 10 percentile. 10 percentile meaning that you want to play safe. Just want to play safe, you choose the bearing that only suitable for safer application. Okay. So equation 18, R equals to R minus P, where P is the probability of the value of X occurring between infinity to X, negative infinity to X, integral of probability distribution Fn between those limits. Accordingly, Fx equals to negative dr derivative over dx. Such for derivative, Weibull probability function Fn is given by this equation. So there are two conditions. The second one is x below x naught, and the first one x is in the range x naught more than 0. Okay, so we'll see how do we use this equation in the example after this. Okay, with both derivative, the mean and standard deviation of fx is given by ux equals to x naught, and then you can read the Euler function, and then gamma r, the symbol r is the gamma function, is found tabulated in table A34. Okay, better you have the textbook with you, better you purchase this textbook. um, you can see what is a table A34, because we are doing some question according to table A34. I just print screen just a little bit. The table is long. Okay, I just print it scale, meaning that when we are doing the calculation, we be using this function r. This is r, and this is n. This is we just use this function. All the function is related to the graph. Okay, mathematicians, statistician know better. Okay, these are related to the graph, meaning that one point, some point of this graph is r. Is r equal to from table A34. Okay, you get from the table A34. Okay, let's see the example. Maybe you can understand better when we are doing some example. Okay, construct the distribution properties of 0 to 30 millimeter deep groove ball bearing if the width parameters are x naught equals to 0.02, theta equals to 4.459, and b equals to 1.483. Okay, you can pause this video, you can go back to the slide. What is the definition by x naught, what is division by theta, and what is the division by b. Okay, and b is the squareness. In the one of the note, it says that b equals to 1.5, near 1.5, more or less 1.5. So in this condition, b is the squareness of the ball bearing, is 1.483. Okay, find the mean, median, and 10 percentile standard deviation and coefficient of variation. Okay, how to find it? Okay, solution for equation 11c, interpolating table A34, the mean deviation line is given, meaning that you should have the table A34 with you. If you have the textbook with you, you can go into the back last pages of the textbook. You can see what is the table A34, and you can get the value from the table. Okay, you interpolate the table, and then you can see what is the value 0.02, 4.459, 0.02, and everything. And then you get the u, dimensional life. Dimensional life is ux equal to this equation, 4.033. Okay, so the average life bearing is 4.0033 life 10 percentile. So the main dimensional life correspond to r 0.5, L50, and is okay. Let me explain what is the average bearing life. So meaning that for the life revolution from the catalog, it is related to the catalog. Just like when you go to the supermarket, when you want IKEA, Tesco, and everything, and everywhere supermarket, they have the catalog. Okay, and you see the catalog, you want to buy fish, you want to buy vegetable, and anything. Okay, okay, this is the catalog when you want to buy the bearing. The same. Okay, it has the catalog. Okay, and then the value that given in the catalog is L10. L10. Let's say L10 is the life in the 10th percentile. In the 10th percentile, this is the 10th percentile. This is the 50. This is the 90 percentile. Okay, so the L10 is given by certain value. Okay, for in order for your application, it becomes the application is times 4.03 times, meaning that it can go for 4 times the value of the life given. That is what means by 4.03. Okay, let's go for the next slide. 10 percentile value, the x 10, 50 percentile. Okay, the 5th percentile value x 0.5, you get 3.487, and then 10 percentile value is equals to 1. Of course, from the graph, 10 percentile is 10 percentile is what safe for the safe value. Meaning that if you choose the bearing for the 10 percentile, you can be sure um, uh, less damage will happen. Okay, meaning that there are you can have option 50 percentile, you can have option 90 percentile, uh, depending on your risk that you want. Okay, okay, coefficient of variance of dimensional life. This is the standard deviation of dimensional life. Okay, and this is given equation, and you get the coefficient of variation of dimensional life is 0.683. The how you can do this question is you trace back the numbers. Okay, trace back the numbers. Where can you get this number 4.4590.02? You trace back, and then um, you should understand. Okay, you should understand. um, I think that's all for the uh, I think that's all for this video. Okay, see you in the next video relating load, life and reliability. Okay, so thank you very much.